So we'll continue the practice test with question 2 of the free response part, where it asks you to find the percentage composition of a couple of different compounds. Remember that percentage composition is always equal to part divided by the whole thing times 100%. And what they mean by part and whole is adding them up on the periodic table. And so I did this one on a separate piece of paper here for both of them. I'm just going to slide it up here and notice that the first substance is 2 carbons, 6 hydrogens, and 1 oxygen. And once again, percent composition is always part divided by whole times 100%. Here's the 2 carbons, 2 times 12 divided by 46 for the whole thing times 100%, so I get 52% carbon. Here's the hydrogen, 6 divided by 46 times 100, 16 divided by 46 for oxygen, and so you end up with 34.8% oxygen. You should be able to add all 3 percents together and get to 100 as well, so that's another way to find the third one. The second part of question 2 was CH4O, and here are the percentage compositions for each one of those. Okay, the next question was stoichiometry problems, and this is problems similar to chapter 482 and 81, chapter 482 and 81. You can see right here is one where we have a balanced equation and we want to calculate a mass, and here's another one where we have a mass and we're reacting with excess chlorine gas. I did both of these on separate paper as well. So here's the first problem with the zinc, and notice the steps that it takes are always the similar stoichiometry steps. Step number 1, write the balanced chemical equation. Step number 2, convert to moles. It's nice because the balanced chemical equations are given to us in all these equations, so we never have to do that step. Convert to moles, that's this portion right here. I got the 65.4 from the periodic table. Next is to use the mole to mole ratio from the balanced chemical equation. There's 2 silvers for every 1 zinc, 2 silvers for every 1 zinc. And then the third step is to convert to whatever units they ask for, and in this case they're asking for the units of grams, so I looked up silver on the periodic table and it's approximately 108. The second one uses the same steps. Convert aluminum to grams, that's step 2. I'm sorry, from grams to moles. 2 to 2 ratio on the balanced chemical equation. And then the units that it asks for are grams once again, so I looked up and added up aluminum chloride on the periodic table to get 133. Question number 4 is solution stoichiometry. It's a similar type of question, but now you might need to use, in these steps, instead of converting to moles or milliliters, you might have to use the molarity triangle to get you to volume or moles or molarity. So in this one you can see they give you the balanced chemical equation and then they ask 2 questions about it. The first one asks how many moles of hydrochloric acid are required, and here's the work for it. Step 1, convert to moles. Step 2, mole to mole ratio, and that's all they asked for that question. The next one asks you what is the concentration, so now you have to take the moles that you had divided by the liters that they give you in that question, so you end up with that concentration. On the next page, it has a very difficult solution stoichiometry problem right here, and this one will not be this difficult on the test, but nonetheless, here's the solution to the problem. It's the lead nitrate and sodium bromide question. So here's the balanced equation. Here's the initial amount of moles of lead nitrate, the initial amount of moles of sodium bromide. You need to determine the limiter, and it turns out that sodium bromide limits, so you'll lose all of that in the change and you end up with 0. In this one, you lose 0.05, so you end up with 0.05 because you started with 0.1 moles. And here you'll gain the same amount as you lose right here because it's a 1-to-1 stoichiometric ratio. And you'll lose, or I'm sorry, gain 0.1 here because it's a 1-to-2 stoichiometric ratio. You need to take those moles then and convert them to concentrations. So to convert them to concentrations, you take the moles and divide it by the liters of solution, and there's a 1/2 liter. moles remaining divided by the liters of solution. This is a solid, so there's no concentration. And then you have to split them up into their ions. That's a difficult part right there, and you can see my answers. I won't spend a ton of time on that because that's not tested, that method on the test. Question 5, balanced chemical reactions and then writing them as net ionic equations. The first one, when you write the net ionic equations, always ask the question, is it a strong electrolyte? And strong electrolytes always need to be split up or dissociated or made into ions. How do you know if it's a strong electrolyte? It's one of three things. Number one, it's a strong acid. Number two, it's a strong base. Number three, it's a soluble ionic salt. How do I know if it's a soluble ionic salt? Well, it's one of those that fits the solubility rules, and there's only 4 solubility rules that you have to have memorized, and they're actually given to you on the test. You need to know that sodium salts, potassium containing salts, ammonium containing salts, and nitrate containing salts are always soluble. They might give you a solubility rule in a question, but these are the ones that you should have memorized, and if you forget to memorize them, lucky you, they're on the front of the test as well. And so going through here, to find out if it's ionic, know that it's got one of these cations right here connected to some kind of anion, or it's got this anion with some kind of cation in it that's not hydrogen, because obviously if it has a hydrogen leading it, it's a strong acid. These guys, if it has a hydroxide on it, it would be a strong base, or at least a soluble base in the case of NH4OH. And so they'll split up as well. So in these guys right here, the strontium nitrate splits up because it's a nitrate containing thing. So you'd write that as Sr positive 2 and NO3 minus, but make sure to put 2 of them there because there's a little 2 down below here. And then the KOH is a strong base, so I split that up into K plus and 2OH minus. And then over here on the right hand side, notice there's a little S there, so that means it's going to be a solid. So don't split it up because you never split up pure solids or pure liquids or pure gases. And then KNO3 is 2K plus 2NO3. And I put a little note on here that will dissolve, so perhaps you would dissociate this one because it is a strong base. And you know, this is probably not the best example, and there won't be one on the test like this where you have to kind of question whether it really is solid or not. But you could split it as well and then end up with no net ionic equation because everything would cancel. But if you have it this way, then the nitrates cancel, the potassiums cancel, and you end up with those two things making a strontium hydroxide. I'll do one other example. Let's do this bottom one right here where it's a solution of a strong base barium hydroxide. You can look at the other answers right here, and of course the answers are all posted as well. And so the strong base is barium hydroxide, and it says it's reacting with acetic acid, and you need to know or have memorized your strong acids. So you know the strong acids are hydrohydroxyl high, honohydroxyl OH2SO4. Do not include acetic acid, so that's going to have to stay together. Going to have to stay together, and it makes barium acetate, C2H3O2, and barium's plus 2 and acetate's minus 1, so you need a 2 there, and then it's going to make some water. Never split up water either because that's a pure liquid. Barium hydroxide, it tells you, oh, first balance the equation, so you need a 2 right here and a 2 right here. A strong base, so split it up into Ba plus 2 and 2 OH minuses. Keep the weak acid together. Split this guy up because all acetates are soluble. And then leave the water together. And then the things that cancel will be the barium ions. So you end up with this as your net ionic equation right down here. Here are a couple of other balancing equation problems. These are 2 combustion reactions. Remember, combustion reactions always make carbon dioxide and water. And it doesn't tell you that in the question that, you know, it's going to make carbon dioxide and water, so you need to know that a combustion reaction makes that. So here you know that magnesium carbonate is going to form, and so a good way to know this is that the cation switches with the cation, so you swap those two, and then don't forget to do the crisscrossing over here of the charges. Here's a silver nitrate one making silver sulfate over here. Don't forget to crisscross the charges again. And aluminum nitrate. Don't forget to do the crisscrossing over here, and then after that you can balance it. This is another one where we swap the cations. This is a metal, so it's always going to be a positive ion. Swaps with this metal. And then we have the zinc and the nickel exchanging places here. And here's an acid-base reaction. And remember, they just want the molecular equation here. You don't have to go and split them up at all. And then on the back side, the very last problems, a few more writing acid-base reactions. The hydrochloric acid and strontium hydroxide, lithium carbonate, sodium sulfite. And these two right here, there are a couple tricky ones. No, there's one tricky one on the test like this. That's a carbonate, a sulfite, or a hydrogen carbonate. And remember, the ones that are gas-forming reactions are the ones that react with an acid, in this case hydrochloric acid, and contain either a sulfide, a carbonate, a hydrogen carbonate, which would just be -1, a sulfite, which is -2, or a hydrogen sulfite, which is -1. And you'll see that this one's got a carbonate in it, so it makes carbon dioxide gas. This one's got a sulfite in it, so it makes sulfur dioxide gas. This one's got a hydrogen carbonate in it, so it makes carbon dioxide gas. So when you write these, you can write them as H2CO3 over here or H2SO3 over here, but remember that they split up into these species right here of water and the gas. They split up, and that's technically not the right name. It actually decomposes into those pieces. Okay, good luck.